In this second lecture of, reactive material balances, we are going to talk about independent species, independent equations, and independent reactions. This is a concept that students struggle with, and it takes a little bit of practice. So let's see. Let's start with independent equations. So, as you know, when you are trying to solve a series of equations to get unknowns, you need to have the same number of equations as you have unknowns. But if those equations are not independent, you will not be able to solve the unknowns. What does that mean? Well, look, in this example here, we have two equations, and you can see clearly that x plus 2y is equal to 4 and 3x plus 6y is equal to 12 are the same equation. If you just divide through by 3, you end up with equation 1. So if you try to solve for x and y in this set of equations, you will not be able to do it. And there are other situations where it's not even as obvious as this first one that I showed you. Here in the second set, you may, at a quick glance, these look independent. But it turns out that if you multiply the top equation by 2 and subtract the second equation, you will get the third equation, which means that they are not independent. So if you try to solve for x, y, and z with this set, you will not get any result. So how does that apply to our chemical balances? If two species, and this applies both to molecular and atomic species, are in the same ratio wherever they appear in a process, balances on those species will not be independent equations. So here's an example. We have ethylene and oxygen forming ethylene oxide. And here we have C and H, everywhere they appear, are in a ratio of 1 to 2. So we only have two independent atomic species. C and O, or H and O, are you can pick two of the three basically, and one of them has to be O. And however, we see, and it may not be as obvious, but we have three independent molecular species. So the same thing can happen with chemical reactions. If the chemical reactions are not independent, if the chemical reactions are independent, if you cannot obtain any one of them by adding and subtracting multiples of any of the others. So in fact, in this set here, there's only two independent reactions. If we multiply the middle equation by 2 and add the top equation, we obtain the third equation. So once again, we would not be able to determine A, B, and C. So let's look at an example calculation. Some of this I'm not going to go through the part that's repeating from before, but I would encourage you to study this. It's in your reader, so look at these and try to solve it. These are opportunities for you to try to solve this problem before I go over it in this video. So look at this problem statement in the reader, try to solve it, and then see how you did, if you got the right answer. If you didn't get the right answer, then listen and see what you did. Okay, so in this problem, the reaction between ethylene and hydrogen bromide to form ethyl bromide is carried out in a continuous reactor. The product stream is analyzed and found to contain 51.7 mole percent C2H5Br and 17.3% HBr. The feed to the reactor contains only ethylene and hydrogen bromide. Calculate the fractional conversion of the limiting reactant and the percentage by which the other reactant is in excess. If the molar flow rate of the feed stream is 165, what is the extent of reaction? Okay, so if we look at this process, we can see that all of the information from the problem statement has been included here in this flowchart. So we have 51.7 mole percent C2H5Br, 17.3 mole percent HBr, and obviously the balance has to be something, and so it's going to be unreacted C2H4. So we want to do here now on this process, as we see, let's do first the atomic species balance. So how many unknowns are there? I see 1. Note that these are mole fractions, and therefore this n dot is an unknown. We also have over here simply x, because the second mole fraction was written in terms of x. So we have 2 unknowns. So we have 2 unknowns, and we have only 2 independent atomic species. C and H are not independent, so you can pick one of those, and then you can pick bromine. So we have -2 independent atomic species. And there we have 0 degrees of freedom. Now let's try doing the molecular species balance. Again, we know we have 2 unknowns. And how many molecular independent species do we have? We have 3. 1, 2, 3. So we can subtract 3 molecular species, but we have to add 1 chemical reaction. And as you see, again we end up with 0 degrees of freedom. So now I'm going to show one more thing in this before I move on. Here we have this. I want you to think about this for a second. Is n dot equal to, greater than, or less than 165? So you should be able to answer that already, because we've talked about that. So how can we tell by looking at this? And I want to make this point that the moles in, when you have a reaction, does not necessarily equal the moles out. Okay, and I'm talking about total moles, not moles of carbon or moles of hydrogen. I'm talking about the total moles. So we can look at the chemical reaction and we see we have 2 moles going in and we have only 1 mole coming out. So I can tell you without any shadow of a doubt that if any of the reaction occurs, then n dot is going to be less than 165. Okay, so how many balances can we write for this system? We said we can write 2 balances, C and Br. So here they are. We're going to multiply, for our carbon in, we have 165 times the mole fraction, and that's going to equal the mole fractions out that have carbon, okay, times n dot. And for the bromine balance, we do the same thing. Bromine in is going to equal 165 times the mole fraction of HBr, and we're going to include every term that has bromine in it on the outlet and multiplied by n dot. Now we have 2 equations and 2 unknowns that we must solve simultaneously to get n dot is equal to 108.77. And I will point out that indeed it is less than 165. Less than 165. So here the moles in does not equal the moles out. And we also get the mole fraction of x. So the remainder of this I'm going to let you work through because it's all just a review. You should be able to do these calculations, and I encourage you to, again, to try it and check your answers. And finally, the quiz is going to be, here we have a process. You've seen this one before, and you have done this already. We did the molecular balances. So this time, I would like you to perform the degree of freedom analysis on this process by both atomic and molecular species. And let's talk about a couple of hints here. You should get the same result, the same number of degrees of freedom for both the molecular species and the atomic species.